begin the afternoon session now. So it's my great pleasure to introduce our next speaker, Saskia Basics. Saskia is an alumni of the Martinos Center, and I think the faculty member that has traveled the furthest to be here from Brisbane. It's, I think, 4 a.m. Brisbane time for her, and just flew in yesterday. So we're really happy to have you back here at the Martinos Center, Saskia. Saskia is an expert on acquisition, analysis, many things, and today she's going to be talking to us about basic data acquisition for laminar fMRI. Saskia, welcome.
Thank you. Great pleasure to be back again. So welcome everyone to the second half of day one. Renzo and I will basically entertaining you, and our topic is basic data acquisition. My first talk will be about basic laminar fMRI acquisition toolkit. Then Renzo will take over and talk about functional protocol optimization. And then he will give you a short walkthrough through the practicalities, calibrations, and adjustments. And I will then talk about high resolution anatomical and vascular data acquisition in the end. And just to give you an idea what to expect. So the first talk will be pretty theoretical. I want to just lay down the concepts again that apply to all EPI acquisitions. And Renzo will basically take that and apply it to the question, okay, what do we do now that we want to do laminar fMRI? And in his hands-on, then he will really go into the nitty-gritty details. And the last talk will be a little bit about theory and a little bit of examples, so to give you some starting point for your structural images. So let's start with the first talk. As John said, my name is Saskia Basics. I'm from the University of Queensland in Brisbane, Australia. And we will basically talk about 2D EPI and extending it to 3D EPI, which is the most commonly used readout scheme in laminar fMRI studies. Then we will talk a little bit about functional contrasts and how they map onto functional sequences. We'll talk about acceleration strategies and artifacts, and a brief summary of data quality and how to assess it. And then we will look at the summary and an outlook. So extending 2D EPI to 3D EPI, just as a reminder, EPI stands for echoplanar imaging. And here you can see a standard 2D EPI sequence diagram. And if we basically cut off there, we have our standard gradient echo or flash acquisition, where we have the RF excitation, so one RF pulse, and then we have the gradients that encode our image, and then we get one echo. And what makes EPI is basically, instead of just repeating this over and over to fill your K-space, you basically continue and acquire a whole echo train for one slice of the image or one plane in a 3D K-space. And K-space really is the representation of the image encoding through the application of gradients. Usually you see it in kind of like this 2D fashion with one readout axis, usually XY, or X-axis, and the phase encoding often in a Y-axis. So if we take our sequence diagram and just look what's happening in K-space, we can see our pre-phaser here. So we basically go in a left top corner. And then we start reading out our first line, which is an odd echo. We turn around and reading out our second line. And you can really imagine this as, like racing through K-space with a little race car driven by your gradients. And you want to fill the whole thing as fast as possible to get your images and to allow you to do actually functional studies. Because that's, I would say, what sets fMRI acquisitions apart from anatomical acquisitions, just that they're really, really fast, so you can measure changes in whatever parameter over time. And just to put down a couple of more names or words, so the echo train length is usually tens of milliseconds long, and it describes how long does it take you to fill one slice or one plane of K-space. And in most publications, I would say people just cut off the corners, because that's what's happening during the image reconstruction anyways. And then you get just the little arrows pointing right and left. But just keep in mind that it's kind of like a continuous acquisition. You probably hopefully are familiar with the signal decay or the defining contrast of an EPI image, which is T2 star weighted. And that means that as you read out or as you race through K-space, the signal decays slowly. And the main contrast is in the center of an image or in the center of the K-space. That defines how the image will look like. And this is defined by the echo time. So whatever the echo time is, it will tell you how the image will appear once it is reconstructed. Just to give you an idea, so basically, as the echo time increases, you can see that overall the signal intensity goes down, but you can also see that certain contrasts come out better. So I would say at 20 milliseconds, pretty flat still, but at 30 milliseconds, you start to get actually quite nice white matter, gray matter contrast. And if we look at the images or the contrast we are looking for, which is most of the times the bold contrast, and classically it's been the bold contrast. Just a reminder that basically, because we have less deoxygenated hemoglobin when the voxel is in an active state, so to speak, the signal is actually higher. And if you ask, okay, what is the maximum or the optimal echo time, where do I get the biggest difference between rest and activation? That's when the echo time roughly matches the T2 star of the underlying tissue. So this is a general principle, and you can also see, let me turn on my pointer. So you can also see here that this is a relatively flat plateau. So you don't have to be at the exact perfect time to get a nice image contrast. And of course, there's also the question, what is the T2 star of the underlying tissue? And that varies depending on the region you're looking at. But it's a good rule of thumb when you set up your acquisition protocols. So as I said, 2D EPI should be hopefully relatively familiar for most of you. And then in fMRI, most people use 3D EPI for a number of reasons. But it's actually the principle you can see, in a reference here. It's ages old. The actual principle of EPI was basically written down many decades ago. But getting it implemented and getting it to work robust was the actual challenge. And nowadays, there's been great work coming from Rüdiger Stirnberg in Bonn, for example. Our colleagues in Siemens, they are working on a work in progress package. So if you're on a Siemens scanner, you can get something there. And there are just a couple of really nice sequences now available for also 3D EPI. So if we remember, if we want to, not just scan one single slice, but if you want to scan the whole brain in a 2D EPI, we, fill one K-space, do our Fourier transform, that can get one slice back. And then we just continue doing this after we have acquired the whole volume. In contrast, in a 3D EPI, we always excite the whole volume. So that also means that the contrast will look a little bit different because we have very different T1 weighting there. So in a 3D EPI, we excite the whole volume, and then we introduce a second phase encoding direction. So in the K-space, we had readout on X and phase encoding on the Y-axis, and here we basically have on Z, which used to be the slice direction, a second phase encoding directions. Sometimes people call it also segment or partition. The field is a little bit muddied there. So, but the principle is basically more phase encoding. And then we start filling this by reading out one K-space plane after the other. But we are not doing a Fourier transform. We can only do this once we have filled the whole 3D K-space. And when we have done that, we can do our Fourier transform, and then we get basically the whole volume as one image. Why do people like that? It's more or less, not a big difference in most cases. But if you look at some studies, you can see that as we go to smaller and smaller voxels, the temporal signal to noise ratio in 3D EPI actually overtakes the temporal signal to noise ratio in 2D EPI. So if you do kind of like your standard experiments, there's no need to, panic and say, oh my God, I have to do 3D EPI now, 2D EPI is totally fine. But I would say for me, the cutoff is around 1 millimeter. That's where I can probably still do both. But below that, it's really advantageous to do a 3D API acquisition. The only example is if you're willing to sacrifice a lot of coverage and you really, really, really want the temporal resolution as well. That's when people go to 2D with, 3 slices or even 1 slice, or even line scanning. So where there's there's only 1 dimension left, so only 1 line that's being imaged. So if you really need to get extreme high spatial and temporal resolution, that's where you would go. But most of the standard laminar studies use a 3D EPI. Okay, so that's how we get an image. And now we have to decide how should that image actually look like. And we are 3 basically functional contrasts, so they come from the biology. I took that nice depiction from Duvernois that shows us, as you know, we measure blood flow, blood volume changes, not directly the neural activity. So if we apply a little bit of Photoshop, we can actually do some nice, insightful animations. So the hyperemia, or the neurovascular coupling, really starts with changes in cerebral blood volume following neural activity. So CBV goes up, and it mostly goes up on the arterial side of the vasculature, and obviously in the capillaries. And the field is still debating how much slight changes on the venous side as well. So once CBV went up, we also see an increase in perfusion or cerebral blood flow. So that means that more blood is entering the capillary bed. And basically on the other side, so on the venous side, is then where we observe the Bold effect, which means that we are sensitive to changes in blood oxygenation. So if you look at the venous oxygen saturation at rest, that's around 60%. So it's not like all the oxygen is gone, just a certain part is removed. However, if you look at the venous oxygen saturation during activation, it actually goes up. So what we see is that the neurovascular response to neural activity is actually kind of like overcompensating. So we're not observing more oxygen being taken out of the bloodstream, we actually see more blood being delivered to the tissue. And on a kind of like MR side, we don't really see oxygenated blood. It's diamagnetic and it really behaves like the tissue. So we're not, we don't see any changes in how much oxygenated blood is in the vasculature. What we do see is deoxygenated hemoglobin. It's paramagnetic and it shortens our T2 star. And during activation, we basically have less deoxygenated blood because it flows faster. And that means we have kind of like less signal loss. That's why we've seen in the curve in the beginning, kind of like a positive signal actually. So this is kind of like the 3 functional contrasts we can exploit in our experiments. And there are actually a couple of sequences that you can use. And we start with VASO because it kind of like maps very nicely on CBV. So VASO stands for vascular space occupancy, and it measures the space that the vasculature occupies. And it does that, or the initial idea is basically to null the blood signal. So that's why I made it here black, and to only measure the gray matter or the parenchyma. That means if basically we have more CBV, your actual measured signal goes down because you have less gray matter. So that's why the contrast in vaso is usually kind of like the other way around. And if you look at the sequence diagram, how is that implemented? We just look at on the left-hand side, which is our vaso image. You can see here an inversion pulse that basically flips around the magnetization of gray matter in blue and blood in red. And then we just wait, and the magnetization slowly returns to equilibrium. And the trick is to basically acquire the image when the inverted blood goes through zero. So if you excite, then you don't get any contributions from blood, and you only measure the gray matter signal. And if you basically, let the magnetization relax further, you can also acquire a standard EPI readout with a standard bold rating. And then, as I said, it's sensitive to T2 star and gives you kind of like the contrast you're most familiar with. And then you can just keep repeating that. And if you do that, you can basically see that you can measure changes in CBV and also signal changes using a classical bold contrast. And then you get these laminar profiles. Basically, the cerebrospinal fluid is on the left, which is kind of like the surface, and you have the gray matter, white matter border, so the deep layers on the right, and you can see that this nice double peak, which many people look for when they study M1, is quite well depicted here. So this is kind of like the first contrast you can use for your laminar fMRI study. There are other ways to image CBV. And this is, by the way, the only slide I'll have on animal imaging. Everything else is kind of like purely human, just because I'm assuming most of you or all of you want to do human experiments. If you do animal imaging, as Josiane has shown, there are way more things you can do. But on a human side, we are kind of like limited of what we can do or maybe want to do to people. But CBV is quite established in the animal literature. It's, I would say, as much used as bold or even more, because it has a couple of nice features. So you see a flash image on the left for reference, and then you see a T2 star weighted image before before injection of myon, which are iron oxide nanoparticles, and they basically shorten your T2 star really, really strongly. So once you inject that, you can see veins and arteries quite nicely depicted. And from the difference or the ratio of these two images, you can also compute what's the blood volume in the tissue at rest. And you can see it's quite high at the surface, actually. So that's where, all the blood is drained through or coming from. And you can also see kind of like the, draining and veins and ascending arteries as well. CBV is useful because, as I said, or as others have said, it has this nice property of not having this bias towards the surface. So you get activation patterns that are more in line with what you would see from electrophysiology. So arterial spin labeling is a technique to measure cerebral blood flow. It's quite commonly used, or it's quite commonly used in general. And the idea is to basically tag the blood that's coming into the brain through application of an RF pulse, and then let the blood flow, kind of like through the vasculature into the capillaries, and then measure once the blood has reached the capillary bed, and basically measure this tagged blood. And through kind of like comparing it to a reference image, you can measure CBF. It's kind of like really nice contrast. The only problem is its TSNR is really, really low. So if you look here, that's a 1.5. That's the only study I could find on ASL with a laminar analysis attached to it. So, oh, there's another one?
One.
Oh, okay, sorry. One of the two. I missed 50% of the literature. Oh my God. Okay, so there are two studies. But I don't know, there are probably over 100 other studies for laminar fMRI. So it's really, really hard. But you can see that, instead of having this slowly rising profile, you get something that has like the highest activity more or less in the middle layers. But I wanted to include it as a, for completeness. I would not recommend to make your first laminar fMRI study with use of ASL. And then basically the most commonly used contrast, and why it is the most commonly used contrast, is using an EPI, which we already do because it is intrinsically T2 star weighted. So we don't need to do anything extra, just acquire the image and it will already have the contrast we want. Sometimes you will see that or read that, at 7T you get a strong extravascular signal. And I wanted to explain that term a little bit because I see it sometimes in the literature and I find it a little bit confusing. So if we put a vessel filled with partially deoxygenated blood, and it's kind of like perpendicular to the B0 field, so the main magnetic axis, you will get, actually at higher field, the strongest like T2 star changes are because of magnetic fields that are outside of the vessel. But they are caused by the deoxygenated hemoglobin inside the vessel. So the signal originates in the vessel, in the sense that's where the deoxygenated blood is, but you measure its effect on the voxels that are extravascular, so outside of the vessel. That already tells you that this contrast is probably a little bit less specific than the rest, because the deoxygenated blood is not just in the vessel, but it actually affects what's going on around it. But it is more specific than most people thought. And I think this is one of the first studies that showed that you can actually imprint the letter M. I would say it's for polymeny onto visual cortex. But again, as we have seen, you get this increase towards the cortical surface, which doesn't reflect known functional architecture. So we know that not most of the neurons are not on layer 1. We've heard layer 1 is actually basically empty. So we know this is not reflective of neural activity. But it is quite a strong contrast. It's very sensitive, very robust, and very easy to use. And we have seen that even David Norris, as a proponent of ways and spin echo, finds many useful ways to use it. Yeah, I think it's a good starting point. If you are really worried about these contaminations from draining veins, people have proposed spin echo EPI. So that means adding a 180-degree pulse to refocus all the signal or all of the phasing from large vessels. So here you can see basically that the signal decays with the T2 star rate of change, but if you apply an RF pulse, you can refocus some of the dephasing, and it is then T2. Oh, it's no longer working? Yeah.
Oh, it's on.
No, it's back. Oh, is it working again? Okay. Oh yeah, let me know. Okay, I stay still.
Right there.
Thanks. Yeah. So the idea is that basically the field around big vessels is kind of static. So you get an average field although the blood is obviously flowing through it, and your average is kind of like the same throughout the whole acquisition. Whereas, what happens in the capillaries and the small vessels that, is much more random, and that's why you can't refocus these parts. And the idea is it's spin echo is T2 weighted, and you get less contribution from large veins. This has also been confirmed by simulation by Camille. So you can see that at 70, which sits approximately here, your strongest signal change actually comes from capillaries, which are about 5 micrometer thick. Whereas in a gradient echo, so in classical EPI, the strongest signal change comes from vessels that are 200 micrometer thick. So these are kind of like the draining vessels. That's why it's a quite appealing contrast. But there's a big but. So it has quite a low sensitivity. Obviously, you're kind of like removing most of the signal long TEs and TR, so it's not very efficient. It has very high SAR, so that's the specific absorption rate. That's how much RF power you can actually put into your subject. And usually coverage is quite small. So it's quite a challenging technique to use. To overcome some of the limitations of spin echo, people thought maybe we could combine it a little bit with gradient echo and get kind of like the best of both worlds. So that sequence is called gradient and spin echo, or GRACE. And it really does combine two things. So it has spin echoes, and it also has gradient echoes in there. And you can see the K-space already starts to look quite interesting. And if you try to get a feeling of what the contrast looks like, it becomes complicated. So depending on, or let's put it that way, kind of like GRACE oscillates between a strong gradient echo weighting and a strong spin echo weighting. And depending on where you put your effective echo time in combination with how your sequence works, you can basically adjust if you want a more gradient echo or more spin echo weighting. As in a spin echo, you have basically your 180-degree pulses. So you are limited to a relatively small field of view that you have to select, which can be good if you're only interested really in one area, and that might make it easier in some parts. But if you're, I don't know, maybe interested in 2 areas, a little bit apart, or if you want to even do whole brain, who knows, then obviously this is quite limiting. But it has a couple of advantages. So here you can see basically the smoothed, bold profile. This is M1 again. And if you look at the GRACE profile, you can see that you again get kind of like this double peak. So these kind of 2 bright lines. Or you can, do Razo, where you get the kind of like a similar profile, and you could even combine Razo and GRACE. But you can also see that the signal change goes down and down and down. So here we are between 1 and 10% signal change. With GRACE, we're between 1 and 3, and for the Razo, it's between 1 and 4. So the moment you add something to a sequence, that usually means you're losing some sensitivity. But you can gain specificity, and as I said, we're looking for this nice double peak. And the blue line is kind of like Razo, and the red line is GRACE. So they have basically this nice kind of like flat shape and then just the 2 peaks, whereas the classical bold has this strong increase towards the surface. So these are kind of like the most commonly used contrasts. If you see them in the literature, one last word, you might think, wait, for bold, we can just do an EPI and it's T2 star rated. But that's also our readout in Vaso, right? Don't we get a T2 star rating there as well? And the answer is yes. So if you have actually the answer is the same for spin echo, but data contributions is a little bit smaller. So the EPI readout introduces unwanted T2 star contribution in Vaso. And that's why you have to remove them via dynamic division. And you can make certain approximations and basically say that only the inverted blood or only in the vaso image, your magnetization is sensitive to CBV, and in a non-inverted blood, it's basically constant. And then the T2 star weighting is the same across both, so it cancels out, and your contrast is sensitive to 1 minus CBV. It gives you kind of like the CBV change. That's why you also have to always acquire 2 images. So in the sequence diagram I showed, we do like a vaso image and then we do a bold image. So one advantage is obviously you can always just analyze the bold data, but the other thing is that we need it for this correction. Okay, I have to hurry up. So acceleration strategies. So what is, why are we here? Why are we discussing this? What is the one single thing we need to make laminar fMRI work? Why can't you just take your usual sequences and just, do a laminar analysis? What do we need?
Resolution.
Yeah, thank you, Renzo. We need smaller voxel size. And as our resolution goes up, our SNR goes down. So this is kind of like a pretty basic example. So we have your 3x3x3 voxels. And if I just, kind of like make the slice thinner, so I'm not changing anything else, I'm just, making the slice thinner, you can already see how, the noise is coming into the image. And obviously, if we go to 0.8 or 0.5 isotropic, this becomes even worse. The other thing is, Nyquist tells us if we want to have smaller voxels, we need to cover more of K-space. So it's actually, we're not sampling K-space more densely, but we need to go further out. That means as the resolution goes up, our echo train length goes up, and usually also our T goes up. So this is just to put that into perspective. If you want to go to 0.5, you are acquiring a voxel that is 216 times smaller than your 3x3x3 voxel. That is a lot. And that's why we're basically at the limit of what the system can do, what the analysis tools can do. And that's why I think it's also sometimes feels very, very hard just because we're pushing so much on this level. And the kind of like unofficial first acceleration strategy, it's not a real acceleration strategy because you're just cutting things off, but it's the one used basically most of the time is, we are not covering the whole brain, we're just doing a partial coverage, these so-called slaps, because that really helps us to get the TR down. And then we apply the usual tricks, so undersampling using either grappa or sense. So they basically undersample K-space, and then we combine information from multiple coil elements for reconstruction. So undersampling K-space means leaving out K-space lines. As I said, we are kind of like, in our race car driving along, and if we only have to cover half as many lines, then obviously we're, twice as fast. And I don't know how many of you have seen the inside of a coil. I put this picture here to, show you these are just really, kind of like electric wire, nothing more, that measure your signals. And then we apply some image reconstruction and get our images. And just to give you an intuition, so basically as we leave out lines, we actually, cut our field of view in half, and we get this ghosting. So these copies of images superimposed on top of each other. And because the coil sits in different locations, one coil might get more signal from that very voxel we're interested in, and another coil might get less signal because it's further away. And based on this information, we can basically sort the signals back to where they belong. So we know, okay, the signal that the coil that is closer, or that's closer to the coil, must be then the one at the back, and the other coil didn't see so much because it's further front. So the signal comes from here. Grappa does it a little bit different. So sense works in image space, grappa works in k-space, and it interpolates the missing lines first before doing the Fourier transform. But both should, in theory, give you very, very similar results. I put SMS in here to clarify. So SMS is for 2D EPI. So if you do a 3D EPI experiment, you're not using SMS. But SMS has made caipirinha quite popular. And caipi is basically a technique to help you. So if you excite two slices at the same time, they just go on top of each other. And you somehow have to tell them apart. You can again use the information from the coil elements, but that's not enough. Or that means you can't really do this a lot. But if you add caipirinha to that, you can basically spread out the ghosting. And that means it's easier to tell apart where the signal came from. And originally, caipirinha was implemented using RF pulses. And later on, it was then adapted for EPI using blipped EPI. Blipped caipi, sorry, for EPI. And to basically, or what's interesting for us is that we can use the same controlled aliasing, this caipi, also for 3D. So although we are not using SMS, we can still use caipi. So sometimes people get confused, but adding a caipi shift to your acquisition is really, really valuable. It will help you a lot. Partial Fourier is another common technique to accelerate. It means we are also just acquiring a subset of k-space, but we're doing it slightly different. So this is our full k-space, and we just leave out, the first, whatever, 3/8 or 2/8 or 1/8. So what they usually tell you is how much k-space is left. So if you select partial Fourier 7/8, then 7/8 of your k-space is still acquired. It's not how much you leave out. And the reconstruction, and that obviously helps you to reduce your TE and your total readout time. And the reconstruction lies on the symmetry of k-space for real objects. So, okay, that projects pretty well. So here we have our full 3D k-space, and if you then do partial Fourier 5/8, we're still acquiring 5/8 of the k-space, and because it's in theory a real object, so the k-space is symmetric along the diagonals. The object is not real. There's motion. There are RF. There's all kinds of things going on, but it's a good approximation. Unfortunately, the scanner allows you to apply partial Fourier in more than one direction, which violates the idea because now we're cutting off here as well. So the question is, where does the data come from to fill these corners? The reconstruction algorithms can do that, but it will cause all kinds of problems. And also keep in mind that, suddenly you're only acquiring 40% of your data. So that's a huge loss in SNR. So basically don't do this. And I think the third, well, this is not a real acceleration strategy. It actually makes things faster and slower at the same time. So instead of, just doing one k-space plane at once, we separate it out in multiple shots. That usually means your TR goes up, but it also helps you to bring down your TE, which can be quite beneficial, especially at 70, because we are higher field, so the T2 star tends to be lower. And it also helps with distortions. So, it's a pretty simple concept, but you have one shot, or you just do 2 shots, or you do 4 shots. So depending on how much resolution you need and how much TR you're willing to give up for shorter TE and less distortions. And for structural imaging, you can even do 8 shots or 12 shots and get basically EPI images that look more or less like structural images. And we already touched on distortions as one of the biggest problems, I would say, in laminar fMRI. So distortions are caused by or are voxel mislocation through the presence of additional fields. So if you look back into K-space, the time it takes, to go from one sample to the next in the phase encoding direction is actually pretty long, because we have to go all the way over and back in again. And this is kind of like, how does Siemens call it again? Echo spacing. Thank you. Exactly. So this is your echo spacing, or the inverse is the bandwidth. And that tells you, or to finish that, basically we are getting a linear phase across or along the phase encoding direction. And the Fourier shift theorem tells us that means a shift in image space. So that's why these voxels are not gone. They are squished together or shifted to a different location. And this is usually caused by bezier inhomogeneities at the front, so the nasal cavities or the ear canals. And that's also happening in standard EPI acquisitions. And it's quite strong. So you can see here, also acquired a T1 weighted image, just created in the outline of the gray matter. And you can see if I overlay that on my EPI image, it's kind of like fits pretty well in here, but at the front it looks, horrible, obviously. And you can choose with the phase encoding direction where the voxels will be shifted. So will they be squeezed into the rest of the brain, or will they squeezed out the brain? But you can also see, if you can look here, it's actually quite a strong effect. So although it's mostly noticeable at the front, here at the basal ganglia, you still get a little bit of displacement. And that really depends. So the voxel shift really depends on the frequency offset, the echo spacing, and the number of phase encoding step, or as I said, the inverse of the bandwidth. And that really, the stronger the bezier source, obviously, the more your voxel is shifted. T2 star blurring, as I said, our signal decays, and that gives us our contrast, but it also blurs the images a little bit. So we are adding a filter on top of our K-space. It's mostly prominent, again, in the phase encoding direction. And it just gives you kind of like blurred images. There's no way to show it in an image, because we can't, or well, could do an EPTI image. Okay. There are ways now to remove that, but commonly you basically have a point strip function that is not just the size of your voxel, but you have contributions from neighboring voxels in there as well. So partial Fourier, as I said, you can do that to reduce your echo time and also your kind of readout length, but it also introduces blurring, and that again depends on the reconstruction algorithm. So if I just simulate it here by just zero filling the missing points, you can see that this is the full K-space, and this is very blurred images. But obviously there are kind of more advanced reconstruction algorithms for that. The most commonly used one is called POX, something something on something something, partial
projection onto convex sets.
Thank you. And it was quite interesting. So this is a really recent study, although that algorithm is kind of like ages old, and they noticed that especially around kind of like high frequency features, so that is features that kind of like vessels which are only like 1 or 2 voxels thick, and where you have kind of like strong contrast changes from one voxel to the other. That's where POX seems to be introducing some artifacts, actually. So it's not only blurring that you get, but also kind of like artifacts here around the vasculature. And also I would say here, like within the kind of like cortex, it's not quite as clear as it was kind of like over here. So that's why overall be very careful when you're turning this on. Nyquist ghosting is another one. So you usually have eddy currents that basically displace our K-space lines a little bit, so they don't, basically the odd and even echoes don't match up anymore. And if you like do it to an extreme, you get these kind of like ghosts in your image. I would say you shouldn't see that. So this should be removed during the image reconstruction. And I don't know, do you have any examples where that's really coming in? Yes, exactly. So I would say like, usually it's not there. Like the renders have figured out how to remove it, but as we like push the system to its limits, it comes back in, and then it's a little bit more tricky to deal with it. And one more is signal loss. So this is a little bit different to distortions. As I said, in distortions, the voxels aren't gone, they're just squished together in a different location. Signal loss means the signal is dephased. This cannot be reversed. And rule of thumb is as the voxel size or slice thickness goes up, your signal loss goes up. So you can see that as I make the slices thicker and thicker, I'm losing more and more signal here. And this is kind of like one of the situations where the resolution going up doesn't actually mean your SNR goes down because your signal is just gone. So there's always an exception to every rule. And the last point is on data quality. So and more specifically on the temporal signal to noise ratio, so the TSNR. I would say kind of like the first data quality term is actually your mean image. So before you start doing anything, please, please, please look at it. If it looks okay, if it doesn't look okay, that means you have to go back to your data acquisition. If your like magnitude image or images don't look good to begin with, and I think that's why we are putting so much time onto this topic, is it's already hard if you have good data. If you don't have good data, it becomes infinitely more harder to do anything. So that's why I always look at your images. Also look at every participant you acquire. It's very, very easy to, have like 5 really, really good ones. And then, I don't know, someone, drags around the protocol and suddenly the phase encoding directions are switched or something like that. It's very easy to make mistakes. And it's kind of like really key to make sure they don't, go through a whole study and you're not acquiring 20 people and then you start analyzing, you're like, oh my God, this is not usable. But kind of like what do people usually do to, kind of like measure the temporal fidelity of a sequence, which is kind of like a proxy for sensitivity, is dividing the mean of the image intensity over time. So the signal by standard deviation. And the signal really depends on the voxel size and the field strength. And the noise can be kind of like thermal noise, motion, and physiological noise. And you can see here that there's a TSNR image, obviously like 130. This is a really, really, really big voxel. But just to show you, kind of like the CSF here is wide, but because there's so much physiological noise going on, it actually has a low TSNR. And some people have already used these two terms, thermal noise and physiological noise. So thermal noise is actually random motion of protons, which then induce currents and receive elements. So this is noise we would also get in a phantom. Physiological noise is kind of like, it's not noise in the sense of, it's kind of like random. It's real physiological processes happening in the brain. It's just that you're not interested in them. And most of them are kind of like respiratory and cardiac activity. And of course, you could say if you're doing a task experiment, then you're not interested in whatever else is going on in the brain, or it's related to homeostasis or whatever. And so if we have a phantom, that's basically the blue solid line, then as we increase our, basically the noise within the image, so this is determined by the thermal noise. If we kind of like, go, for example, to bigger voxels or something, then the TSNR, so the noise over time, also increases, or the noise goes down, the TSNR obviously increases. If we do that in a human, we are reaching kind of like a plateau, which means that although we have kind of like perfect, SNR within the image, the TSNR doesn't go up anymore because we are seeing all these other processes that we can't remove. I think it's not, or I would say within, kind of like, or below 1 millimeter resolution, we are really in this regime. That's why I call it thermal noise regime, where, if you reduce your thermal noise, you can see an appropriate increase. And again, oh my God, hello.
finicky.
It is. Oh, there it is. Yeah. Is it back? Okay, sorry. Thank you. Okay. Yes, this is the second last slide. So we gain from increasing image or reducing image noise, increasing SNR. And so how does like a common laminar fMRI acquisition look like? So we want to do high resolution, which means usually sub-millimeter. Usually it's a 3D EPI acquisition, but obviously because we have higher temporal SNR than 2D. Usually we also have a little bit lower SAR. I haven't talked too much about that in the like better slice profile, so just some nice benefits there as well. I would say what you see in the literature is somewhere between 0.7 and 1 millimeter. As I said, the TE is not set in stone. You have some flexibility there. If you choose partial coverage, you can get your TE down to 2 to 3 seconds. So that's the acceleration using either grappa or sense. It's usually around 4. And some people use partial Fourier, some don't. Obviously, the current limitations are the image fidelity, so the blurring for 0 and T2 star, and obviously the resolution. So you can see that, I mean, it's pretty cool for, 2 or 3 second image, but it's not perfect. And so how do we get to the perfect image? I don't know. We will see. So Siemens has been working on a new gradient. I think they call it impulse gradient now, which is in Berkeley. I think Magdeburg has one as well. John has one now, coming. So that gradient is basically just a head gradient, which means you can go faster in your little race car through K-space because you don't have to worry about stimulating, kind of like the nerves around your heart or anything, because it's only just a head. So we'll see. Then there are kind of like a couple of initiatives, going to higher and higher field strength. So David Norris is building a 14 Tesla scanner. I also put the 3T down after discussion with John because maybe we just take everything we do and put it back to 3T and our lives would be so much easier because, higher field strength is great, but it also comes with a lot of challenges. So who knows? For example, distortion's obviously much worse. Maybe.
There's like we should both should be waiting. I don't know for the rest. People always talk about field strength only as a function. It's not. Actually, this particular responsible function should change. Comment on this.
Could you repeat the question?
So the question is about macrovascular weighting of field strength.
Saskia, for everyone in Zoom, you just repeat those two.
Sorry, Zoom people. So the question was about how does the weighting of macrovascular and microvascular signal change across field strength? This is a complex one. Because as I said that, so you have kind of like microvasculature and macrovasculature, but then you have also extravasculature and intravasculature. And at higher field, basically the intravascular signal is gone. And that's why, I think that's part of why people thought that, it's better to go to higher field because then you don't get kind of like signal from large veins because the signal within there is gone. But you still have the extravascular effects. So, yeah, I don't know. I would say we need some like realistic modeling on that, to be honest. Because also I'm always struggling a bit, with these kind of like perfect cylinders that, once you put them parallel to B0, all the signal is gone. That obviously never happens either. So yes, some people say, higher field is better for more like microvascular weighting, but then, everyone sees the bias towards the surface, which obviously comes from microvasculature. So I don't know. It's a tricky one. Yes, and yeah, and I put kind of AI here. I've just seen some pretty cool pictures of they were kind of like first tests, so I can't show them. But I think also Renzo will talk about Nordic. So everything that brings down our like thermal noise limit, which is actually kind of easier, I think, than reducing physiological noise, because engineers deal with thermal noise all the time, so they know exactly how to like deal with that. And I think if we can do that, maybe we, in a couple of years, your standard protocol will be 0.5, and everyone will be like, oh my God, these studies in the 2020s, what are these people thinking? You can't even resolve a single layer with that. So we'll see. I think with that, I want to thank John again for inviting me. Obviously the crew for organizing, people I talked to and who taught me about this stuff, my team in Brisbane,